Okay, so this diagram here, we've got our nucleon number on our horizontal axis and we've got our binding energy on our vertical axis. So I'm going to just explain what this is all about. Let's just start off with this first element over here. Now, hydrogen, regular hydrogen, has just got one proton. There's no bonding within that nucleus. All right, it's just a hydrogen. It's got one proton, one positive, nothing else. But then we get something called deuterium, which is your H12. Now, in that, you have one proton. You've got one proton, and you've got one neutron. So there's some binding that's actually taking place in it. Those two are bound together. Now, if I took the mass of that, if I took the mass of this one proton, one neutron, and I found the mass of that, let me call that M1. And then I also took the mass of the proton and the mass of the neutron separated, all right, individually, and I call that mass 2. We would find that mass 2 is greater than mass 1. All right, it loses energy. It gives off energy when that actually occurs, and there's actually a mass defect there. There is a loss of energy in that. Now, we can work out the energy from that by using our E is equal to mc squared. So if I call your M2 minus M1, if I call that delta, that's my change in mass, then my E is equal to my change in mass times c squared, and I would get a certain energy value. Now that energy value would correspond to the binding energy, for those nucleons. Now here, this is the binding energy per nucleon. It's for 1. So let's just have a look here. I'm going to say that the binding energy here is 1. All right, it's just above 1, but we'll take it as 1 mega eV. So the binding energy per nucleon is 1. For 2 of them, it's obviously going to be 2 MeV. So this energy, it's actually going to come from the mass defect, is actually going to equal about 2 mega eV. All right. So what actually happens basically is that these two particles drop down an energy well. They both drop down this energy well where you've got your proton and your neutron down this energy well. And this energy that's given out, it's become at a lower potential energy. They're more stable. And if I wanted to drag them apart, if I wanted to say, okay, I'm going to have you there and you there, to separate them, I would have to put in my 2 MeV to pull them apart, and the mass of those things, that would be changed into the mass. So we view mass as a form of energy. Mass energy changes, and it's related to the binding energy of the nucleon. Now, yes. Yes, so we're going to look at that, because these ones over here, as these ones go this way, now if iron is your most stable element, it's actually got per nucleon about 8.8 mega eV. So there's a very strong bond between its nucleons there. Now as iron starts to get bigger, like when you go to gold and so forth, it actually becomes less stable, so you actually have to put energy in. And that's what happens in the core of a star. As you go past iron, when they start forming these bigger elements, it actually starts sucking in the energy from the star. There's no longer this pressure from the energy being given out, and the star collapses and you get a supernova occurring. That's your supernova event. We'll look at that a lot in both the relativity and astrophysics section. Yep. Okay, so the 2 MeV over here comes from that for the deuterium, for the 2 and the 1H, it's 1 MeV per nucleon. You see, it's per for 1. So there's 2 nucleons, so it's 2 MeV for that molecule. Okay, let me just explain. So let me just I'm just going to now go on to this one over here, our helium. Look at the same procedure here. Now for the helium-3 isotope, it's got 2 protons. It's got 2 protons and 1 neutron. Now we've got about 2.5, roughly about 2.5 mega EV per nucleon. So the total binding energy here, the total binding energy for this, for the helium-2-3, the energy total binding energy is going to be about 7.5 MeV. Okay. Now, what happens when this forms to go to this, and we're going to look at this process. You see here that the binding energy becomes stronger when we take hydrogen and we put it into helium. It gets stronger, and that energy that is given out is your energy of fusion. All right, you're getting a fusion reaction taking place, and this is what happens in a star, is that you take hydrogen, you take these ones over here. Now, I'll give you the whole nuclear synthesis of this. I'm not going to do that now. But if you get 2, 1, and you get hydrogen, plus another 2, 1, and you make a helium over here, it's actually a longer process than this, but let me just say I'm doing that. All right, I squash them together and I make that. The binding energy of this is much greater than this. If I took the mass of this, if I took the mass of the He, and I call that M1, and if I took the mass of your H over there, and I called that equal to M2, then if I took M2 times 2 M2, because there was 2 of them, and I subtracted my M1, I would get some mass. All right, I would get a change in mass, and that would be the energy, and that would be the binding energy now that is increased. So this energy here, there has been an increase in the binding energy. Energy has been given out, and that's given out. That's your energy of fusion. Now you can see here, when you're going from helium to lithium, you've got a massive release of energy. All right, this is huge amounts of energy that are being released. I mean, you're going from 2.5 per nucleon to coming on 6 per nucleon. So you're getting a massively more stable element in lithium, and that when that happens, there is a huge amount of energy. So when stars get enough gravity, the force of gravity becomes large enough, especially with really massive stars, they can actually do that. They can cause that to happen, and you get these massive amounts of energy. And this is what happens all the way up. Here we see, this is interesting, I didn't mention this before. This is our helium-4. This is our regular isotope of helium. Notice how much it is there. It's 7.5. So forming helium within your nucleus creates a massive amount of energy that's been given out in the form of energy. Now this goes on, so you get your carbon forming, your oxygen forming, all the way to iron, which is your most stable. This is the most stable that you can get. And then you start getting less and less stable. They start losing. They're pretty stable still, but they actually, the binding energy gets less and less. And then when we are at uranium, so uranium over here, and we split the atom, when we go this way, This is your fusion. Sorry, this is your fission. This is fission. When we go that way, we get fission. Now, these are dividing, but you can see as they divide, the binding energy increases. And that increase in the binding energy means that they're becoming more stable. They are giving out energy. And those are your fission reactions. Those are the things that are happening in nuclear bombs and nuclear power stations.